Okay, let's have a look at the first one here. All right, so the first one is a pretty standard elevator question. Okay, we're told the mass of the elevator, 600 kilograms, as well as the person inside, and both of them would accelerate at the same rate. Okay, an elevator is a dangerous place if the elevator and the person inside accelerate at different rates. Okay, you're bouncing off the walls of the inside of the elevator if that's the case. All right, so what we're told is that there's a force pulling up. That force is tension in a cable. Okay, is what they tell us. The elevator cable exerts a force of 5.2 times 10 to the 3 newtons. So that's 5,200 newtons. All right, what force is this? Gravity. Okay, because it's pulling down. And that'll be m times g, so that'll be 600 times 9.81, which will be 5886 newtons. Okay, everybody all right with that? Which way is the elevator accelerating? Downwards. Okay. So my next step here, if I want to find the acceleration of the person, is to say, all right, F net equals the vector sum of all forces. That would be the force in the cable plus the force of gravity. The force of gravity being negative because it's downwards. Okay, everyone all right with that so far? All right, so now I'm doing the vector sum of all forces. Okay, so I can simply go m times a equals the mass times the acceleration from the cable plus mass times the acceleration due to gravity. All right, now I already know what m times at is because they told it to me. It's 5,200, and I already calculated what m times g is. It's 5886. So I've got 5,200 plus negative 5886, which will give me 686 newtons in a downward direction. All right, now I've got my net force, okay? So that equals m times a. All I have to do is divide that by m. So my acceleration will be 686 newtons divided by 600 kilograms, and that should give me my 1.14 meters per second squared downwards. Okay? Everybody all right with that? Okay, did I do those same two steps I told you to do in any Newton's second law problem? Vector sum of all forces and m times a, right? Every single time those two forces are going to happen. Okay, question number 2 is a bit different. Question number 2 is an example of what we call the differential acceleration method. That sounds really complex, but it's really not. Okay, what we have to do in a differential acceleration problem is we actually don't get all the forces. We're going to use the accelerations instead. So we're going to go vector sum of all accelerations equals the net acceleration, which is still true. Okay, vector sum of any things together is going to be the net of all of those things. Okay, so that's what we're going to be looking at for this one. What I want you guys to do right now is draw the free body diagram for this question. Okay, you're not going to have all the numbers obviously, but draw the free body diagram as best you can right now. Okay. Okay, so our free body diagram for this one has a box with a question mark inside of it, because I have no idea what the mass is. That's what the question is asking me to find. Okay, there's this engine that's being lifted up by this chain hoist. Okay, is this still an elevator? Anytime you lift something or lower something vertically, it's an elevator. Okay, it's just in this case it doesn't say elevator, but even throwing something up in the air is still an elevator question. Okay, so I've got the applied force of the chain hoist, which they tell me here is 2,850 newtons. Okay, and what other force? Force of gravity. Yeah. Okay, which is m times g. The other thing they tell me is the overall acceleration is 1.50 meters per second squared. Okay, that's actually my net acceleration because it's the result of the net force. Right? If something accelerates, it's because there's a net force. That's the acceleration caused by the net force. All right. So now I'm a bit stuck because I'm trying to find mass, and that's different. We haven't had a question where we had to find the mass yet.
Sorry, where would we put the acceleration?
Right now, I just put it off to the side. It's a number that I have, but I don't have use for it yet. Yeah. Okay, so I know one of my steps has got to be that F net equals m times a. And that a is the net acceleration. I also know that F net equals the vector sum of all the forces. So there's the force of the hoist plus the force of gravity. Okay? Again, those are the two steps we said are going to be in every Newton's second law question. My problem is that I don't have mass. So here's what I'm going to do. I'm going to expand this out. Mass times the net acceleration is my net force. Okay? For this force, the mass times the acceleration the hoist could produce by itself, okay, will give me the force of the hoist. I already know that number, but that's how I would calculate it. Okay? Plus the force of gravity. Okay? Now, you're probably going, there you're like going in circles. You're not getting any closer to the answer. You're just writing more crap on the board. Yes. And it's going to get worse. Because I'm going to do something that's completely counterintuitive right now. I'm supposed to be solving for mass. What's in every term in this equation I just wrote? Yeah. What can I do with something if it's in every term? I can cancel it. Now again, this is where it's counterintuitive. Why would you cancel the thing you're looking for? I don't want to spoil it for you. Okay, wait for it. Okay, but right now, I'm going to take mass right out of here. I'm going to cancel it. So now, I have that my net acceleration equals the acceleration the hoist could produce plus the acceleration due to gravity. Why does this help me? It helps me in this way. I was given that number, and I know that number. Can I solve for the number I don't have? Okay. If I solve for this number, which I can do now, I can go back to this and say the force of the hoist equals mass times the acceleration of the hoist. I was given this number, and I'm going to be able to calculate this number. Will that help me get the mass? It can. Okay? This is really convoluted, okay? But it's mathematically valid, okay? But it is convoluted. We don't usually give too many of these. Like I've never put a differential acceleration problem on a test, okay? But it's still valid to see, okay, how that works. And that really what we're trying to show here is that the vector sum of all forces is also like the vector sum of all accelerations, okay? Because they go together and they cause each other, they're both true. Okay, everyone kind of follow my reasoning there? Okay. All right, so what we have now is the ability to calculate the acceleration of the hoist. So the acceleration the hoist could produce will be my net acceleration minus the acceleration due to gravity, right? I'm just bringing acceleration due to gravity over to this side here, okay? All right, so I'm going to have my net acceleration, which was 1.50 meters per second squared up, minus my acceleration due to gravity. downwards, so I need to make it negative. Right? Okay, so when I do this, okay, I'm going to have 1.5 minus negative 9.81, which is the same as adding 9.81, which should give me 11.31 meters per second squared. Okay, if there was no gravity and only the hoist acted on the engine, that's the acceleration the engine would have. Okay? Everybody with me there? All right. So now that I know this, and I know that the force in the hoist was 2850, because they told me that here in the beginning, now I can say this. The force of the hoist equals mass times the acceleration of the hoist, and I now know both of those numbers. Okay, now I'm solving for the mass of the engine. 2850 divided by 11.31 should give me 252 kilograms. Okay, very convoluted, right? But the most complex mathematical operation we had to do was dividing two numbers. Okay, we had a little bit of algebra in there, but okay, that was about it. So as long as we understand that the relationship between net force and all the forces that contribute to it is the same as net acceleration and all the accelerations that would contribute to it, we're good. That's what we need to get out of that question. Okay, every force can produce a corresponding acceleration if it's by itself. Okay, so anytime we say vector sum of all forces, okay, we're saying, all right, so I've got force 1 plus force 2 plus force 3, okay, that's the same as saying this, mass times my net acceleration equals mass times acceleration 1 plus mass times acceleration 2 plus mass times acceleration 3, okay? Forces are always calculated by multiplying the mass by whatever acceleration they could produce, right? And so this then is also true. My net acceleration is acceleration 1 plus acceleration 2 plus acceleration 3, okay? They're all vector quantities. We add all vector quantities in the same way. Therefore, these three relationships should be true. Okay. Where did I lose it?
Where do I start?
Okay.
I don't know.
All right, so let's just go back to the engine, okay? The engine's being acted on by two forces, right? The force of the hoist and the force of gravity, okay? If I didn't want to deal with the forces, if they told me, here's the acceleration of the hoist and here's the acceleration due to gravity, if I add those together, I would get the net acceleration. Okay, well, the same would be true if I put in the same number for m for both of them. It's the same mass, right? So I'm multiplying both of those numbers by the same number. Their factor changes by the same amount. One more time. Right. In the end, I'm not going to ask you on a test to do a differential acceleration problem. I just want to point out with this example that the vector sum of all forces and the vector sum of all accelerations for the same problem are both true. Okay, so this is a differential acceleration problem, but it's about a skydiver. The person who jumps out of a plane is still an elevator because they're moving vertically. Okay, hopefully they're not moving up. You jump out of a plane and go up, okay, you got big problems. The plane was probably just upside down, okay, when you jumped up, so you weren't really moving up. Okay. All right, so this guy jumps out of a perfectly good airplane, okay, and now we got to figure out what the mass of the skydiver is. So this problem is exactly the same as the one we just did. Okay? Instead of a hoist and gravity, we have air resistance and gravity. Right? This thing is accelerating downwards where the hoist was going upwards. Right? So see if you can do this one. It's the same type of problem as the one we just did. All right, give you a couple minutes on that. Okay, so here's the start of this one. They already did our free body diagram for us. Okay, we got the skydiver here. We have the force of friction, air resistance, acting upwards, and we know that that force is 250 newtons. And then we have the force of gravity acting down, okay, which is going to be m times g. We don't know what m is, so we can't actually calculate a value for that yet. The other thing they tell us is that the actual net acceleration of the skydiver is 5.96 meters per second squared down. So if you jump out of a perfectly good airplane, you don't actually accelerate at 9.81 meters per second squared. You would for like the first half a second or so, and then air resistance would start piling on, and the faster you go, the greater air resistance becomes until you reach terminal velocity. Maybe you've heard that term before. Okay? Terminal velocity is the maximum speed at which you can fall. Right? You won't ever go faster than that because air resistance, the force of air resistance, balances out the force of gravity. Those forces become equal, and as a result, you can't accelerate anymore because the net force has become, what number? 0, exactly. Okay, so when you reach terminal velocity, you don't accelerate. If you don't accelerate, it's because the net force is 0. So there's a speed where your force of air resistance and the force pulling you down due to gravity equal, and you stop accelerating, and you just fall at this terminal velocity, which is really fast. Okay, it's still enough to make you flat as a pancake, but you're not going to go any faster than that speed. So this idea that we accelerate all the way to the ground is not what happens in the real world. Okay, it's what happens in the perfect physical world, but not in the real. Okay, so this guy's just jumped out of the plane. There's some air resistance and some gravity still accelerating. Okay, so here's what we got. Vector sum of all forces. So F net is force of friction or air resistance plus gravity. Okay, I don't know what the force of gravity is, and I can't calculate it because I don't have mass. I do know what this one is because they told me it's 250 newtons. So what I'm going to do is expand this out like I did the last time. Okay, mass times the net acceleration equals mass times the acceleration due to friction plus mass times the acceleration due to gravity. All right. Mass is in every term here, agreed? Okay, so I'm going to cancel it off. That's going to leave me with my net acceleration equals the acceleration caused by friction plus negative 9.81. Okay, well, sorry, time plus g. I'll just put g in there. Okay, plus g. All right, I want to calculate this one because I know what g is and I know what the net acceleration is. They gave it to me. So I'm going to go net acceleration minus g equals the acceleration caused by the force of friction. So that'll be negative 5.96 because it's down minus negative 9.81 because it's also down. That's going to equal the acceleration produced by friction, which will be a positive number, and it should be. That force is which way? All right, so now I'm going to have 5.96 minus negative 9.81. What does it come out to? Did anyone else punch it in? Good? 3.85, okay, just to save us time. Okay, so this comes out to 3.85 meters per second squared up. All right, so now I know the acceleration due to friction. And I know the force of friction because they told me what it was. All right, then that means that this relationship is true. The force of friction equals mass times the acceleration friction would cause. So now I can calculate the mass. I'm going to say 250, my force of friction, equals mass times the acceleration due to friction. So mass times 3.85. All I have to do is bring the 3.85 over. I'm solving for mass. Okay, so mass of the skydiver, right, 65 kilograms. Again, we're not going to get a lot of differential acceleration problems as long as you understand the relationship between all the accelerations and the relationship between all the forces is the same. Their vector sum results in a net. Okay? Okay. give number 1 a try. It's not a differential acceleration problem, it's just a simple elevator question. Right? I'll make it a little bit bigger so you can read it better. Okay? Give that one a try. Give you a few minutes on that. That's it. Okay, so let's have a look at this one. This is, again, a pretty basic elevator question, not a differential acceleration problem, right? We just have a bungee jumper, okay, whose mass we know, 55 kilograms. We know that the bungee cord, at the instant they want us to do the calculating, is exerting 825 newtons of elastic force upwards. What other force is acting on her? Gravity. Okay, can I calculate how big gravity is? Yeah, m times g. So 55 times 9.81 will give me my force of gravity there. So 539.55. Okay, so this is a good bungee jumping situation. The force of the bungee cord is greater than the force of gravity. It's about more than that. You have to make sure the bungee cord is the right length. Otherwise, it doesn't matter how much force it exerts upwards, it'll stretch too much and bad things will happen. Okay, so we want it to be definitely having a net force that is upwards, and we clearly have that. The 825 is larger than the 539. Okay, so if I want to calculate the acceleration, the first thing I need to do is find what is my net force. That'll be the vector sum of all forces. So that'll be 825 newtons up, okay, minus or plus negative 539.55 newtons. So 825 minus my answer. Okay, so 285.45 newtons is my net force, and it's upwards. All right, so now I know what net force is, 285.45. Okay, that is my vector sum of all forces, and equals m times a. Right? I just have to divide by the mass, and I'll have my acceleration. So that 285.45 divided by 55, right, 5.19 meters per second squared up. Yeah, okay. Gotta make sure we put a vector on that. Okay, so 5.2. I think we only have two significant figures there. So 5.2 meters per second squared up. Everybody okay with that one? Okay. Now for number 2 here, okay, it says during the bungee jump, the velocity of the 55 kilogram woman is at the lowest point is 0. Not because she hits the ground, but because at that instant the cord has stretched its maximum amounts and slowed her to a stop before yanking her violently upwards. Okay, because that's what happens in a bungee jump, right? You jump off and you have this moment of free fall until the bungee cord starts to stretch, and the bungee cord slows you down, slows you down, slows you down. It's like the opposite of jumping upwards in the air, right? This way you slow down, you get to your most stretched point, and then boing, okay, you get shot back upwards from the elastic force of the bungee cord, all right? And then you kind of oscillate for a while. Okay? If you've ever watched somebody bungee jump, right? They fall, they get shot up, and then they fall, and then they kind of just oscillate for a little while, and then they lower them down or raise them back up, whichever is most appropriate. Okay? All right, because they used to do this at West Edmonton. Well, I don't know if they still do. In the World Water Park there, they still do? Yeah. No, I think it was going. One went bad. Yeah. All right, so for part A here, it says compare the direction of her acceleration at the lowest point of the jump to the part of the jump where she is accelerating due to gravity. Well, she's only accelerating due to gravity for the first part of the jump where she's in free fall. Once the bungee cord starts to stretch, okay, she's now starting to accelerate upwards. Okay, so at her lowest point, her acceleration is definitely upwards. Okay, and that's all they're asking there. Okay. Trying to decide whether I want to start systems with you today or not. I think I don't want to yet, okay? Is that, I know you're looking at this and going, oh man, that looks really hard. There's 2 blocks, now what do I do? It's really not that much harder, but, okay, let's take a 5-minute break, and then I'm gonna have some questions on the board from the workbook that I'm going to want you guys to try that are kind of like what we've been doing, okay? If you're leaving the classroom, make sure you're quiet in the hallways, okay? Back here, 108. Okay, so what I want you working on here, guys, is the first worksheet in the Dynamics worksheet booklet, okay? So it's on like page 2, okay? And it starts out with really simple Newton's second law questions, like the lacrosse player one we did yesterday, like that kind of easy, okay? And it's gonna get a bit trickier as you go along. Some of them are gonna ask you to do an acceleration calculation before you do the Newton's second law problem, okay? Nothing you guys can't handle, you just have to use your acceleration formulas from the last unit, right? But you guys should be able to handle 1 through, well, when there's elevator questions on here, you guys shouldn't have any trouble with anything up to probably 19, okay? After that, we start getting into pulleys, which are systems, and inclined planes, which we haven't talked about yet. Okay, so you guys shouldn't have any trouble with any of the ones on that first page. In fact, you'll probably just burn right through the first like 10, okay, because they're all pretty straightforward. So I'm going to give you some time on those. If there are any that give us trouble, then just ask, and we'll walk through those ones together. Okay, this is kind of getting our feet under us in terms of the basics of Newton's second law. Okay.